Hello, dear. Good morning and welcome back. You have started watching video lectures on machine learning, and today we are going to discuss a very interesting classification tool and perhaps one of the most sophisticated tools we have studied so far in the area of classifications. Yes, you are right. We are going to discuss today about support vector machine. Well, what is a support vector machine? Why it is called machine? All and what is the background and how it is different from many other classification tools which we have studied. Slowly we are going to discuss about them. So basically, the first question will arise that we have studied so many classifiers, for example, logistic regression, decision tree, then neural network, and you see again what is the use of another classifier. Nearest neighbor also you have studied. The main theme is actually this is based on a very sophisticated idea. And what is that sophisticated idea? This is also, you see, binary linear classifier, inherently linear classifier, and which classifies data with maximum possible geometric margin. So this is the uniqueness. Okay, maximum possible geometric margin. So we'll focus our discussion on this. Then we're going to study about who invented actually the concept of support vector machine. Then slowly we'll go deeper and we will discuss the following: support vector machine as a maximum margin classifier, then formulating the classification problem as a constrained quadratic optimization problem. This is very unique thing about support vector machine, because here classification problem has been, for the first time I think, has been formulated or modeled as a constraint, as an optimization problem, constrained quadratic optimization problem. And since the uh, quadratic optimization is very well developed and very rich optimization tool, once you can formulate your classification problem as a quadratic optimization problem, then you can use the ready-made tools for solving the optimization problem, and these are available. So that is another uniqueness. So we'll talk about what primal problem is, and then we'll try to solve a problem, small problem by hand, so that you can actually get confidence about how a support vector machine works. Then we'll discuss why primal problem solution is not enough and why we need to formulate a dual problem. Then what is KKT condition? Then we'll talk about the kernel function, okay, because support vector machine is a linear classifier, but having so much of sophistication which we are going to discuss, we do not want to confine support vector machine uh, to classify only, to act as a linear classifier only. So using kernel we can enhance its capability, and then we will discuss some algorithm like SMO algorithm, uh, which are used, algorithms like SMO algorithms are used for training a support vector machine. So we are going to discuss all of them. But at the beginning, who actually invented the idea and what is new here? You see, we have so far studied many classification tools. For example, I have, say, the features x1, x2, and say I have some samples of negative class and I have some samples belonging to positive class. Then you see you have studied nearest neighborhood, nearest neighbor. So nearest neighbor classifier will try to classify perhaps something like, it will draw a decision boundary like this. Then you also know that how decision tree works. So then you also know that neural network. So a straight line, which is a decision boundary, can be drawn here. It could be drawn here. It could be also drawn like this. So these are the different kind of classifier which will do the same classification task in a different way. Nearest neighbor, decision tree, neural network, all in their own inherent way will try to classify. Okay, and what are characteristic feature here? You see, it's not guaranteed. You have drawn some decision boundary, a straight line here, but it is not guaranteed that it will say. Now I will talk about what say. Oops. Okay. Maximum margin. Okay. So suppose same again. I have some positive samples belonging to positive class, some sample belonging to the negative class, and this is our support vector machine, which is trying to draw maximum margin classifier. So my classifier is here, and this is the gutter, okay, which is separating the two classes, samples of the two classes. So what is advantage here? Obvious. Okay. Advantage is, you see, this could be biased with negative sample. That means if negative sample has a little bit inaccuracy, then it will be misclassified. Same thing decision tree also. Same thing neural network also. So neural network could give you this, could give you that. All kind of possible decision boundary will give, and those are vulnerable for misclassification, because any problem with the samples, some inaccuracies in the samples which are there is a chance of misclassification in all the classification tools. Okay, including, I forgot to tell you, including that the way parameter is determined in case of logistic regression also will not guarantee the maximum margin classifier. So maximum margin classifier has obvious intuitive advantage. What is that advantage? That if I can somehow draw a decision boundary which will be equidistant from both the classes, say this is my negative class and this is my positive class. So if my decision boundary, which is here, is equidistant from this class and this class, then that is perhaps optimal decision boundary, isn't it? Because that can be robust. So even if your negative sample is somewhere here or here, or your positive sample is somewhere here or here, still this decision boundary will classify appropriately. So that is the advantage of maximum margin classifier. Okay, and that is guaranteed by support vector machine. So it's a great idea actually. Okay, and we like the sophistication of the idea. That means your classification problem you are formulating as an optimization problem, constant quadratic optimization problem. And then you are using optimization problem solving tools to crank out the solution. Okay. So the credit goes to actually Vladimir Bapnik, a Russian scientist. Okay, he did his PhD thesis in 1974. So idea is not new. In 1974, his PhD thesis was all about the support vector machine. But at that time, you see, the computation power was not that great, and sophisticated training algorithm were not developed. So although he invented this, these were not exposed to the outside world till he migrated to United States, and there he joined ATA and TBL lab, and in 1995 he actually showed that how support vector machine classifier, he demonstrated how support vector machine classifier can solve many real world problem more efficiently. More specifically, during that time, United States Postal Service were trying to automate the address sorting problem using computer vision. Okay, you see, in those days, people used to write a lot of physical mail, and you see, lot of handwritten addresses were written, and manually those letters are to be sorted out for the destination, and it took a lot of time, and it was prone to human error. So US Postal Service were desperately trying to automate this process. That is how to read, so for example, pin code correctly, because pin code is the first protocol of the address which is read when your physical mail starts its journey. So Vladimir Bapnik used support vector machine to classify the hand digit um, recognition uh, more effectively using support vector machine. Earlier, people are using neural network, and he demonstrated that support vector machine, the efficiency of it will be much more than a neural network, and that was the um, starting of the journey of support vector machine. Thereafter, okay, he wrote another paper on kernel and how to club kernel with support vector machine, and then there are a lot of excitation among the scientists because it has a very good mathematical foundation, or we can call it analytical tool. Uh, the basis of support vector machine is an analytical tool which many scientists love. And then, of course, many sophisticated training algorithms were being developed. One such algorithm we'll study a little detail called SMO algorithm was developed in the Microsoft research. And all these actually brought the support vector machine to the limelight, and people started using it as an off-the-shelf problem solver. Okay, and they called it machine, just like machine. You give your problem, machine will solve it. Okay, very quickly and very efficiently, and you will be surprised in late 90s, early 2000. Okay, it completely overshadowed the so-called fully connected neural network as a classifier. So that was the success of support vector machine. Okay, now let us try to understand a little bit and go a little bit deeper that how the problem uh, was formulated, or intuitively how you can formulate the problem of solving classification using a maximum margin classifier. Say here, this This is a picture. These are two features. This is another feature. Okay, feature x1 and x2, and you have uh, two class. Two classes. One is negative class, another is positive class. Okay, and support vector machine is a binary classifier. Means it can classify. It can draw a decision boundary between two classes. Now you see intuitively. So our idea is, we have talked that the specialty of support vector machine is that it gives you the maximum margin between the samples, and at the boundary. So this is just like a gutter, and at the boundary, the samples are called support vectors. This is also support vector. Okay. So once you can somehow identify that who are the support vectors of the two classes, then you can draw a kind of gutter which is touching upon those support vectors, and that's it. And at the middle of the gutter, you can draw your decision boundary so that it will be robust, in the sense that if there are some samples, negative samples even here and here, this will still classify that those samples belong to negative class. Or if some samples are here and here, so still it will classify that those belongs to positive class. So that is being guaranteed in support vector machine by formulating a constant quadratic optimization problem, which we will slowly uh, show you how it is doing. Okay. Now, for the time being, see, suppose we are drawing a vector W. Okay, so W. Okay. This vector is actually perpendicular to the gutter, and also as such, it will be perpendicular to the decision boundary or the straight line. In 2D, decision boundary is a straight line. In 3D, of course, it will be a plane, and in more higher dimensional feature space, the decision boundary will be higher dimensional hyperplane. Okay, so that you can um, conceptualize only. Now let us see. We have only two features, so it's a planar problem. We have two class, and then uh, I have drawn one vector which is, and say hypothetically I know that these are my support vectors, so I have drawn this. So I'm trying to formulate the problem. Okay, the way Bartnik actually uh, tried to formulate. So first draw a vector W which is perpendicular here. Now consider any sample, okay, somewhere, arbitrary sample, and the position vector of that sample, say, is V. Okay. So you see, if I draw the, if I want to um, make a projection of this vector on this W, which is perpendicular to this gutter, then what we can get, right? Dot product. So it will be a quantity, scalar quantity, right? And now you see, I can make a decision, right? Say, if it is greater than equal to B is some arbitrary constant, then the arbitrary sample belongs to positive class. Otherwise, it belongs to a negative class. Huh? You see, for example, if the sample is here, still I will have the I will have the position vector, okay, and I will take the projection. Say it is here, and this is my position vector for the sample, which is here, negative sample. Okay, and I will take a projection, and if it is less than some arbitrary constant I have defined, if it is less than that, then it is in the negative class. If it is greater than some class, that means if the sample here, the B actually is determined, or threshold bias, which you can call, is determined in such a way that intuitively this uh, decision um, rule can be formulated, and this is very intuitive, right? So you any arbitrary point you are taking, you know the representation of that point in the form of vector, and then you are trying to see its projection to a vector direction which is perpendicular, which you have drawn as a perpendicular to the gutter. Okay, and we have introduced a constant called B to take a decision in which class it belongs. Isn't it a great idea? Very simple, right? So, in the next class, we'll actually go deeper in modeling this as a classification. This is classification problem, and we'll try to model it as a quadratic constant optimization problem. We'll start from here. So, stay tuned. Wish you all the best and stay safe. Bye bye.